I am Luca. I'm so excited to be here. Thank you so much for having me. Um, so today we'll be talking about exploring the TTC delays with reproducible data science. Yeah, so I guess the first thing we probably want to go over before anything is kind of what is data science, because it's kind of a buzzword. A lot of us kind of think of it as it's kind of been around, like being thrown around in the media, being thrown around online. So maybe let's try and kind of we can try and unpack a little bit. So basically, there's a few kind of interesting notions of like data science, and kind of like one way to look at it is it's a science. So like, you know, just like chemists do cool things with chemicals, physicists do cool things with like particle accelerators, data scientists will do cool things with data, you know, like, you know, you're supposed to look like Tony Stark, like kind of doing fun stuff like that. But you know, the reality is more like that. But, you know, like I mean, that's kind of under romanticizing it a little bit. But like the thing is really is that data science is a little hard to define because it's really informed by a lot of different things. But in essence, really, data science is about like kind of systematically organizing data with testable explanations and predictions, just like science would do the same thing with like chemicals or like with matter or with like computers or whatever other things that science tests. And because of that, because of it being so general and wide-reaching, it intersects with so many different academic fields. It can intersect with economics, physics, statistics, computer science, gender studies, English, really anywhere that you can find data. And now that we have computers that can analyze text data and sound and so many other modalities of data, there's really no place that data science doesn't touch nowadays. Which brings us to the kind of what data science is today. So really the problem with data science is that a lot of the methods and models that especially social science researchers in economics and psychology, a lot of the methods are really actually unverifiable. A lot of like there in a really interesting blog post, there was a really famous statistician, Andrew Gelman, that kind of talked about the reproducibility crisis in social science. In essence, a lot of studies done in psychology were found to actually be completely unreplicatable. So really, like psychologists would do these experiments, they would collect their data, they would do their experiments, and but there was never ever a way for them to actually, like, they never really published their data, so nobody could actually check whether any of it was true. The other problem they found is that many of the members of like the American Psychological Association, where he was writing about, because I mean, he's a statistician, so there's a lot of beef between different social science disciplines, but that's kind of unrelated. But essentially, like, that he kind of talked about that psychologists were kind of coming up with different statistics to kind of feed their results. So really, they're generating knowledge that doesn't actually exist, or that we can't actually verify at all. So that's kind of the issue with not having research that's reproducible. Like the funny thing with like with more physical and natural sciences is that you can kind of say, okay, if I mix these two chemicals together, I should get X. And someone can just go, okay, I'm going to go and get those two chemicals, mix them together. Let's see if I get X. If I get Y, then we know that that theory is just not true, right? And really, that's what kind of the problem was. So if we can't really check if something is true, how do we know it's true? That kind of brings us to reproducible data science, and that's really kind of like the next frontier, how a lot of social scientists and information professionals, which is kind of like my field of study, like are trying to like revolutionize, I guess. Really, reproducible data science is like one of the information professors has said, really is just research that can be done using all the materials that you used to make it. So whereas chemists have different chemicals, data scientists have, well, data. So really, reproducible data science is about being able to share the data that you have with everyone, to be able to come to hopefully the same conclusions that you do about the data that you've got. And yeah, at minimum, really being reproducible in data science is about releasing your code, releasing your workflow, and releasing all the data sets you've used in your analysis. So, and like, for instance, in what I'm going to show you in a few minutes, all the data sets that I found were found through a Open Data Toronto, which is an open database of basically data that's collected by the city of Toronto for people to use. I use a reproducible workflow that was based on a U of T professor's design to kind of analyze it, basically based in a bunch of different tools that I'll go over. So, and these are all openly available tools and open source tools that people have access to, like R, like GitHub. These are all things that people can just like access and get an account for free. And yeah, really the main thing is that reproducibility, like in the sciences, like in the natural sciences for social science and other sciences that don't have like physical matter and more like data, reproducibility allows for like critique, remixing of ideas, making sure, even more banally, just making sure that like your methodology and coding was correct. Because like there could have been assumptions that you as a person, just with your lived experience, you might have created a graph with a certain perspective that perhaps someone else from a different background may not have even thought of or could have a different idea on. And so being able to just have the materials that you use to create the knowledge that you did allows for people to remix it, to critique it, and to intersect it with different ideas. And this idea of removing the gatekeeping from like a lack of data sharing allows for different fields, not only like data science, but also fields that it intersects with like economics, sociology, gender studies, even English. And it allows them to advance these fields faster and allows people to understand more about them. And yeah, so that's kind of like the primer on reproducible data science. And now I guess I can show you a little bit about how I used it to kind of understand the TTC delays. So basically the reproducible data science workflow that I use was based on a design by a U of T professor whose name is Rohan Alexander. He's very cool if you ever get to meet him. I hope you do eventually, if you can. But basically the idea is that you kind of start from the basics of like what you want to do. So first you kind of plan kind of what you want to analyze. So for me, it was kind of easy. I wanted to know what delays, like the different causes and different things, basically the different determinants of delays in the TTC system. So really it starts really rough. So like just sketching graphs, kind of understanding like what sorts of, what's your goal in essence. So part of that, and then it then is kind of converting that to code. So all the workflow that I did was done in the R Studio language, where then I took a lot of the graphs that I did and essentially tried to simulate the data. I didn't even like touch the data before that. I was just kind of like trying to figure out, okay, so what's my final data set going to look like? Because you want to kind of have a kind of shining light of like where you want to end up. So first you have the graphs, then you have your final data set. Then you finally actually get to the actual data, and that's kind of where the fun begins, because lo and behold, data science is about kind of analyzing data that's super messy and unstructured, and often that just means kind of you have to be kind of the comb to the messy hair that is the world to try and understand it better. So for me, how I did it is there's a particular extension to the R language that allows you to download the data from this database and acquire it. So, but the reality was that within my paper, I analyzed like 3 different vehicles. There's like, streetcars, subways, and buses. But the reality was that they had 3 different data sets. So I had to download all those 3 first, and then I had to do kind of the exploration, which is kind of the fun coding part that I kind of mentioned at the beginning, where basically you have to go through and you have to like drop different columns. You have to make sure that you essentially have to make sure that like all the data can fit together in a coherent package for you to actually analyze, and then create the actual graphs that kind of go from it. And then finally, you can then kind of share your kind of findings with it, either like how I wrote a paper on it, or like now I'm actually here presenting it to you guys. And like I said, these were kind of the software tools I use. And all of these, the most important thing with reproducible data science is to make sure that the tools that you use are open and available to everyone. So R is a language that is open source, and was created by a guy named Hadley Wickham out of like New Zealand, I think. Yeah, New Zealand. And basically the idea was is that it was a language that academics, but even people by extension who just wanted to learn like data analysis skills to be able to basically in order to analyze these data. So all of these stuff, basically RStudio, Quarto are basically part of the same thing, that they're like these open source tools that anyone can download. And then GitHub is something that's really available to pretty much like in small quantities, you can upload code that then you can display in a public repository, which anyone can see. And so with these tools, you can then you then have a workflow that allows people to, first allows you to reproduce, to analyze data in a way that, first of all, not only other people will understand, but also you in the future will understand, because it's all systematically kind of organized and allows you to like come back to a certain spot at a certain time, but also more importantly allows other people to also review it in the same way that you do and understand it as well. And yeah, so I guess I'm just going to go over a few of the main findings of it. Actually, no, before that, I can just show you, I can give you a little bit of an idea, hopefully, of this is, I might have to reshare my screen. Just give me 1 second. I wanted to just show you the GitHub repository of just to show you how it was organized, because it's kind of interesting to try and get an idea of like how in practice how you actually achieve like the reproducibility of it. So here essentially you have like the folder. Basically what you can do is like through R natively, you can like write all of your code and then upload it from like your project file on your computer to like a database, similar to like how like if you have like a cloud service like Google Drive or something else, you can kind of like drag and drop files. In a similar way, you can do this with code. But the difference is that with GitHub, you just continually overwrite the code so that if something happens to the code, you can go back to a previous state. That's the only difference between like GitHub and something like Google Drive. But yeah, so the organization is pretty easy. It's basically like inputs. It should be easy basically, because in that way anyone can understand it. So first you have like your inputs. So like this would be like your raw data. You have like, you have your like large language model output. So like if you have like ChatGPT, you want to make sure that like all of the different tools you have are like kind of shown to people. And then also your rough sketches, and then just like, then you also then have like your clean data, which you manipulated in R. So the important thing also is to show like the progression from like your raw unstructured data to like the actual data that you use to do your analysis, to see, so that people can then also see that progression as well. And then so you have like the clean data set, and then finally you then have the paper as well, which is like kind of written in Quarto, which is like kind of it's sort of like coding a paper in a way, where it's like it's written in it's another thing, but it's not really important. The important thing is that you get the paper at the end, because the paper is sort of like the actual advertisement for your actual analysis. Like it just presents the analysis in a pretty way, but really the interesting part is like delving into it and actually seeing the difference. Anyways, so now I guess I can show you some of the results, because I think that's probably what most people are here for, I think. Probably. Feel that after. So I found a lot of really interesting things actually about the TTC delays. That were some were pretty expected, some were a little bit unexpected though, which a few were expected, and then a few were oh, sorry. Close your eyes. Okay. So a few were interesting, and a few were like kind of not like we're kind of expected, and a few were unexpected. So the first thing I found was kind of the difference between the different delays of the different types of vehicles. So here, interestingly enough, the data provided by the TTC on subways didn't actually provide a reason for a particular delay. So I had to omit it here. But for buses and streetcars, they provided the same type of kind of language of delays. So what we found is that like among buses and streetcars, mechanical delays were kind of the highest. Then along with operations, which kind of deals with people like switching and whatnot, and then also diversions, which was quite surprising actually that like over 2023, there were over 20,000 delays of mechanical instances, which is like, when you think about it, perhaps it may be something to look into in terms of like the durability of the trains, or maybe something else. As someone who isn't like super familiar with it, but as someone who's just a data scientist, it's something to look into. Another interesting one is to actually look at like the number of incidents by the type of vehicle, and then also the average delay time in minutes by the vehicle. What's kind of cool here is that we can see that in both instances, buses are just delayed across the board, which kind of makes sense because they're on the road. It's kind of chaotic. There'll be like there's always going to be like either a cyclist or like a car. There'll be someone that'll get in the way. So there'll be something else. What's interesting though is that although streetcars have the lowest amount of delays in 2023, they actually have the second highest like delay time. So if something happens to a streetcar, they tend to be delayed for longer on average, even though that the delays don't happen as much. This was kind of surprising, was that how delays, the number of delay count per month, like essentially went up throughout the year. So starting in January was like the lowest amount of delays. And then by December, you actually had more delays than you do in January, which is kind of, so like in the winter, in January, you'll have lower delays, but in December, as the year progresses, you'll get higher and higher amounts of delays per month. And this is true across all the different means of transport. But there wasn't really anything conclusively to explain why this happens, but it would be something also, again, to look into further. This was probably the favorite graph that I did, which was the average delay time by vehicle, because what you can see here is like subways obviously have kind of like the least amount of delay times because there isn't really that much that can happen to a subway to make it delayed. But what was interesting is that with streetcars, you can see the delays skyrocketing around this time of the year when the weather gets warmer, cyclists go out onto the road, more people are out, and then that causes more delays for streetcars that are crossing through intersections or get blindsided by random people. Even eclipsing that of like bus delays, which we knew were like kind of like the most delayed overall, which I thought was quite cool. But yeah, so a couple of these graphs kind of present a few kind of like implications, which is like, since buses are the most delayed, it would kind of make sense that we deploy buses on the routes that kind of need them the most. And if you go into the paper, I kind of go into more detail about like which routes are most delayed and which aren't. But the idea is that like you could deploy buses on routes that are more delayed, or implement tactics like bus bridging, which is essentially taking buses from lines that are like relatively underused during a certain time of the day and then put them on lines that are relatively overused. The other thing you could do is hopefully try and enhance like the training of different people and then increasing staffing on the weekends, because another thing that I found was that delays tended to be higher on the weekend, which might have something to do with like higher volumes of people. And then also kind of the other thing is then also to report the delay reasons of subways, because subways they tend to have the highest instance of delay. We actually have no reason why. There's never a reason why a certain subway has gotten delayed for a certain reason. So maybe improving data collection tactics would also shed more light on like why subways could be delayed in a particular way, and then kind of being able to like come up with a solution to solve that. And then finally, just ensuring that like training programs and strategies are kind of effectively deployed during the warmer months, as like people are more outside and there's tends to be more people on roads that could disrupt the streetcar traffic. And all of these are kind of, they're really general policy questions. They're really kind of general policy implications, because I'm not a politician. I'm not really a specialist, say, in transit, but What I do know is how to analyze data. So I can tell you, like, okay, something is more delayed. So with my limited knowledge of, well, with my fairly okay knowledge of things, because we've all ridden the subway, so we do have kind of a relatively good understanding of how the system works to a degree. We can say certain things about how we could possibly improve it in a practical way. And yeah, so really overall, in conclusion, basically the idea of using reproducible data science is that essentially, if you wanted to now, you could go to my repository online if you knew R, or actually even better, because R is an open source language. This is the beautiful thing about it, is that you could even use something like ChatGPT or Claude or any of the other AI models and be able to write scripts and tell it to write scripts that can analyze my data set in R. Or better yet, you could even just plonk it into Excel. If I've met most of you have probably used Excel once or twice in your life. So you could even just using my data set that I've cleaned, you could go and then hopefully come to the same conclusions as I have. And then probably even come up with more interesting conclusions than I have as well. But the idea is that essentially reproducible data science is the idea that anyone should be able to understand the world around them. And through creating reproducible data science, through creating reproducible data sets, we can hopefully allow other people to understand the world like we do, and then that should lead to a better understanding of the world as a whole. As we all know, knowledge is power. And being able to understand our world will allow us to create better solutions for it. And hopefully, using some of the stuff that I've talked to you about, we can come up with some solutions together now. So thank you.